we've got stream 3 entering that node, we've also got stream 10 entering that node, and stream 4 going off, so m.3 plus m.10 is m.4, and so that's the equation we have here. And similarly, we can write the balances on the other 3 nodes. So we can write balances on that distillation column, on that filter. We can also write it on that splitting point here, and so on. So that's the set of equations that we have, and we can see that we actually have 10 unknowns. Right? We regard each stream in this process as being a variable that we need to solve for. So we have 10 streams, so there are 10 unknowns. We so far have described just 6 relationships, so we need another 4 relationships if we want to solve the system. And this is what we have available in the way of that, that the feed rate of raw material to the process m.1, that's known to be K1. In other words, that's a known quantity. Then we also do know the required product rate, right? If we look at the process here, our product rate is this stream here. If this is our primary product, stream 5, then we typically know what production rate we require. So here we say m.5 is equal to K2, where K2 is some known, in the same way that we do know the flow rate into the process. So those 2 things are known. And then if we also know the separation efficiency here, in other words, if we know how effective this distillation column is in separating the stream 4 into a gas and into a liquid, in other words, what's the ratio between 5 and 6, then that's a third piece of information that we can embed into our framework here. The last thing is an internal split ratio. So down here we can see stream 8 splitting into streams 10 and 9. So we can identify that split ratio as being K4. So these K values we'll just regard as some known constants, and so these 10 here are indeed relationships we can use to determine all the unknown variables in the system. So looking at the system of equations, you can see now that there's significantly more work to be done in developing a solution. Right? We could solve these things manually or by hand, so to say, but we can see that, and it's not a terribly difficult system of equations, but that requires a significant amount of effort, and we wonder if we can't do this more efficiently using a matrix. So let's try and do that. Let's pose the system as a vector matrix equation. So let's say here that we try to create this form here, right? There's some vector of numbers, a vector of mass flow rates, which we'll just call M here. So that's a column of unknown values, and there'll be some matrix that we'll use to help us develop the set of equations, and for each equation on the right hand side we'll have the value that's stored in B. So if we look at this proposal here for A, M and B, we'll find that this corresponds to our system of equations. So in this matrix A here, you can see on the top row you've got 1, -1 and zeros, and there's a 1 over there. And then down this column of M's here, we've got the elements of, well, we've got all our mass flow rates written in. So you can see if you multiply matrix A by vector M, if we were to look at the first row, for instance, if you multiply that row down that column, you can see that you'll get there m.1 minus m.2 plus m.9 being equal to 0, right? It's matrix A times M equal to B. So you look at that row multiplying down that column being equal to the vector B. So if we're looking at the first row there, then the right hand side will be this value. So we're saying m.1 minus m.2 plus m.9 equals 0, and if we look at our system of equations, that's the same as this equation here if we took m.2 onto the left hand side, right? So that's the same equation that we have for this form here, and similarly for the second one, you can see here if you multiply this through, you'll get m dot 2 minus m dot 3 is equal to 0, and that's the same as this, as saying m dot 2 equals m dot 3. So that's how you can represent it in your matrix. And let's just look at another 2. Let's look down here. You can see m dot 1 equals k1. So in contrast to these equations, this equation contains some number which is not in an m dot. So here this part can sit on the left hand side, but we have to use the right hand side for this part. So if we look here, this I guess is the seventh relationship, and you can see here the seventh relationship. You've got m dot 1, right? 1, this row here multiplied down the column, only the m dot 1 will survive, so m dot 1 equals, and on the right hand side, k1. So that's how we've got that equation into our matrix. And let's just look at this one. M dot 10 equals k4 m dot 9, and of course we can rewrite this as m dot 10 minus k4 m dot 9 equals 0. And looking here, so that's m dot 10, the last position on this row, m dot 10 multiplied with m dot 10 minus k4 times m dot 9 being equal to 0. That gives us the same equation that we're looking for. So we've successfully composed our system of equations as a system of vector matrix equations, and now we have available to us all the power of linear algebra to analyze that and to develop a solution from. Right? Of course, since we have created this form here, matrix A times M equals B, that this holds because we've got all those equations which hold, right? If this is true, then the vector M must be the same as the inverse of matrix A multiplied with the vector B, right? And we'll do it that way first, looking at matrix inversion, just for the sake of simplicity. We do appreciate that matrix inversion is not the most efficient way to solve the system of equations, and we should in principle be using LU factorization or QR factorization to do that. But for now, let's just work with matrix inversion. So we've got our matrix A, and we want to invert that matrix. So let's first of all just pull this information into our Matlab command window. So I'm just going to copy all these statements here, right? This matrix A is quite the same as the matrix A we've been talking about. So we've just coded this up. You can see here we've created this vector of k's for k1, k2, k3, k4, and we've created the vector B here, the right hand side vector, and of course that's a column vector, so we need to transpose this row vector. And then matrix A is exactly the same as this matrix that we developed up here. So let's just paste that code into the command window. Let me just clear this old work, close all, clear all CLC, and so that's created for us our matrix A, our vector B, and we can solve for our matrix M. Our vector M. So we said M must be the inverse of A multiplied with B, and if we do that, that's the result we get, right? And remember, we had ordered M such that where is it here? So such that we have all those mass flow rates written down the column there, and let's look at the values. You can see in this position we've got 100 here, and we knew that. We had specified that the mass flow rate to the fresh stream into the process was 100 kilograms per second. M.1 was 100, so we have that result there. We had also required that the primary product stream be 60 kilograms per second, so we can see that that's been retained there. And of course, if we look at the process, going back to the diagram here, you can see if we imagine